You can also model an on-grid PV system with an AC coupled battery system. You go to the type of the system window and select the PV system with electrical appliances and battery system. After defining consumption and model your PV system and select the inverter you want, you can select a battery system. We have defined what is a battery system, but again, just to remember, a battery system is a solar battery inverter, a battery, and a solar charge controller. You can select a complete battery system here, or customize your own one by editing those data. In this example, we have a 2 kW solar battery inverter. The maximum charging power is the maximum power the inverter could supply for the batteries while charging for only 30 minutes. It could be the same as the power rating or 25% at maximum more than it. With the same concept, maximum discharging power is the maximum power the inverter could handle while discharging the batteries for only 30 minutes. Also, it could be the same or 25% or less more than the power rating to avoid errors and losses at the simulation. See, if it's more than 25%, you will see a warning sign. Those information are usually provided by the manufacturers. You can edit the efficiency curve here too. Okay. Now, this is related to the charge controller, the charging strategy. Now, what is I-charging? I-phase charging happens when the battery is deeply discharged around 10 to 20%. The battery is charged by the maximum current a charger could accept, and the voltage of the batteries is increasing gradually until it reaches the rated voltage of the batteries, as for example 12 volt, 2.4 volt, or 24 volts. Once the voltage reaches Vmax, which is 70 to 80% of the capacity of the batteries, it may stay there for an amount of time or quickly enter the U node or V node charging. At this stage, the battery capacity goes from 80% to 90% or 95%, but in a different way. The charger keeps the battery's voltage constant, as the batteries have already reached the rated voltage as 24 volt or 12 volt or whatever, and starts charging at an exponentially decreasing current until the current reaches a minimum value and the batteries are at 90 or 95%. Third stage is U phase. When you connect the charger for a long time or weeks, the voltage of the batteries drop to a safe value that doesn't reduce the lifetime of a battery and also could be connected on a charger for weeks. And also, a very small current is applied by the charger. So the charger supplies very small value of current and decreases the applied voltage on the batteries to let them drop to a slightly lower voltage that is safe for weeks. The small value provided by the charger compensates the self-discharge of batteries. At this stage, the batteries will be kept near to 100% of its capacity. Also, this stage helps the battery stay fully charged for weeks. Here, using the datasheet of batteries, you define the start of I-charging and the end capacity of it. Also, the U node or V node charging and what is its duration to go from 80% to 90%. Trickle charging is the U phase charging. It should be within the limits of full charging. Full charging is charging under constant or Vmax voltage and at decreasing current that when reaches I minimum, the voltage of the batteries drop to start trickle or U charging. According to the batteries manufacturer, you should charge batteries from 90% to 97% in 5 hours each 14 days to save its lifetime or to maintain their performance. And it's an example. The data may differ from a manufacturer to another one or due to different models of batteries. Equalization charge is done to remove sulfate crystals on the batteries which are lead acid ones, as it decreases battery's lifetime. Also, it's done for maintenance. You let the batteries rise from 97%, for example, to a level of 100% in 10 hours each 180 days. So each 180 days or half of a year, you should repeat this cycle. Now, you define the charge controller strategy according to the batteries also. You can also change the batteries and re-change the charging strategy. Select a battery or define your own one, then OK. Now, how would you size the batteries? According to surveying, you should know the amount of energy consumed by the loads in kilowatt-hour daily, or an average value, and estimate the night consumption in kilowatt-hour. After you know their information, or this information, the energy required by batteries is E night divided by the efficiency of the batteries plus E night plus E day divided by the efficiency multiplied by the days of autonomy. The days of autonomy is the days when the batteries have to supply the load alone or all the day's load, as the array or the modules may go under maintenance or modification. So the batteries have to supply all of the load and not the night load only. Then, you have to decide the days of autonomy or just set it to 0. BV-Sol gives you E-battery multiplied by the efficiency known as usable battery energy. So after deciding the usable battery energy, you have to calculate the ampere hour of the batteries. Ampere hour equals to E-battery divided by DOD, or the depth of discharge, or the maximum capacity that could be removed from the batteries to help keep it a long lifetime. This number is multiplied by the battery's rated voltage or the system voltage. DOD is recommended by the manufacturer, so now you can have the ampere hour or the C10 rating. If you have 120 ampere hour battery and it's C10 rated, then it could be fully discharged in 10 hours under 12 amperes. You can't exceed 12 amperes. It will reduce the lifetime significantly. Most solar batteries are C10 rated, as it needs fast discharging and charging rates to be capable to deliver high energy in short time. Now, if you know the ampere hour, adjust the number of batteries per string and the number of strings to obtain at least the ampere hour you calculated or higher, and at least the amount of energy you need or the usable energy. Let's have a quick example. We need 10 kilowatt hour from batteries, and the depth of discharge after we deliver this energy will be 70%, and we select 48 volt batteries. They are 4 connected in series of 12 volt battery. We need at least 297.6 ampere hour. This connection is not acceptable, it's below the minimum. Let's select higher ampere hour battery. Let's select the 101 ampere hour. Then we increase the number of strings. Now we got a higher ampere hour and also 10.2 kilowatt hour of usable energy, which is acceptable. Remember, the voltage or the battery's voltage depend on the inverter and the energy required. Now you can move to the next step.